So we're going to start chapter 5 today, and we're going to start by taking a look at the natural logarithmic function, and specifically at differentiation. So depending on what type of calculus course you take, this is sometimes done earlier in the curriculum, like back when you actually learn all the derivatives the first time around. This is sometimes done over there. These are called transcendental functions, and so if you see a course or hear the phrase early transcendental, it means this is done sooner. Calculus is one of those very interesting creatures that are just not done in the same way from university to university. So our book puts it in here at this place, which is why we encounter it here. So I would like for you to remember the antiderivative of what we get when we have a power function, x to the n. So the antiderivative is we add 1 to the exponent and we divide by the new exponent. And we always put plus c for a general antiderivative on the end. And this is clarified very specifically when we learn it, but you probably don't remember, that it works as long as that the n, right, the exponent is not -1. So think about what would happen if we tried to use this property and n is -1. So you take -1 as the exponent, you add 1 to it, and you get 0. And then you would try and divide by 0, right? It's undefined. So that is an undefined operation. So clearly that's not how we have to do it. There must be another way to do it when the x's exponent is -1. So what happens? So what do we have happen if the x is -1, or it's equivalent of asking what if the integral, what do we do with the integral of 1 over x? That's the same question. And we're going to introduce this as the definition of what a natural log is. So the natural log of x is the antiderivative of x to the -1. That's its actual definition. Now, I imagine you've seen natural logs before, and nobody ever defined them this way. You probably saw them in Algebra 2 in high school. It's usually where they make their first appearance. But nobody defined them that way for you because you didn't know what derivatives and antiderivatives were, so it didn't make any sense, right, to do it that way. It wouldn't have happened, and it wouldn't have worked. So it's not defined that way initially. However, that is what a natural log is. It is the antiderivative of 1 over x. The domain is the set of all positive real numbers, and you will see this notation used, this r with these double lines on it. When we write it, you usually see it written with just the double line on the left for the real numbers. Plus means the positive real numbers, okay? So using this definition and thinking about it from an antiderivative perspective will lead us to the same graph that you would have seen presented in the Algebra 2 class from back in the day. So the graph looks something like this. It crosses here at 1. And along the y-axis, you have an asymptote. So it's not going to be perfectly drawn there, otherwise you won't be able to see it the way that my red is marked. I'll move it over just a little bit, but this is an asymptote over here. That's not too bad. And there's a lot of features of this graph. Some more important than others, but these are features of this graph. First one mentioned, the x-intercept's at 1, 0. That's one I drew in. And second one is that it has a vertical asymptote at x equals 0. That's the third one, I guess. The second one is that there's no y-intercept. It doesn't have a y-intercept. That's why we have the vertical asymptote at x equals 0. We describe the behavior of this graph as increasing without bound. Okay, so what does it mean to say without bound? Well, it means it never ends. It never ends. It may not be looking this drastic the way that I've drawn it, but it never ends. It never has like a horizontal asymptote that's trapping it. That's what this really means. It's not trapped by something else. So the notation for increasing without bound that we saw in Calc 1 is that the limit as x goes to infinity of this function ln of x is infinity. Okay, so as we trace along, if we want to mark it like this, if we trace along here and the x value goes to infinity, then the y value is doing the same. Not as fast, actually, but the same. The domain, then, is 0 to infinity. Okay, it's on the right-hand side. It's the positive graph, the positive side. So you could also say the domain is all real numbers that are positive, like that. That was what I mentioned on the previous slide. The range is actually everything. So remember, range is the y values, and you can see it goes up forever, it goes down forever. We get all the y values that we want. We could actually say that the range is R. It's all real numbers. The graph is continuous. You don't see any gaps, any jumps, any holes. There's no picking up of the pencil as we draw it. It's 1-to-1. Now, that's not a topic that we've probably spent very much time talking about recently. But what 1-to-1 means is that every x value has a y value and every y value has an x value, right? They're in a 1-to-1 correspondence. They pair up perfectly. We'll talk more about 1-to-1 another day. And it's concave down. We did talk about that in Calc 1. Right? The concavity is that this is opening downward. Now, just like in like a college algebra or an Algebra 2 course in high school, there are manipulations we can do to this function, and we can do things like shift it left and right, move it up and down, stretch it out, shrink it up, flip it over axes. We can do all of those kind of manipulations, and that's what we're going to do first. So you will see throughout this first chapter especially that we're going to intermingle a lot of algebra concepts in with our calculus concepts. The directions said that we were doing, the title of the section said we were doing natural log differentiation. We'll get to the differentiation. But we're going to look at the algebra components first as a reminder. So some of this stuff is going to look familiar, and maybe familiar, but you still don't remember it. That's okay. But that's kind of the point, is that it's been a minute since you've looked at these things probably, so we're going to refresh you. All right, so if you take a look at this one, this is f of x is negative natural log of x plus 2. Now, yes, you have a calculator. You should be able to verify what we're about to do on the calculator. That's fine. But I'd like for us to talk about what these features are doing, what these different pieces are doing to this graph. Let's actually start inside the parentheses, because order of operations usually kind of thinks about it like that. X plus 2. Do you remember when you have a plus 2 inside with x grouped like that? Whether it's a quadratic or a cubic or a square root function, and now we've got natural logs. What does that do to the graph? Okay, it shifts it. It's either going to shift it left or right because it's inside with x. But it actually doesn't shift it right. It shifts it left. So inside pieces of addition and subtraction do the opposite. They're very interesting. They're not intuitive. So we're going to shift this entire graph to the left. So to the left 2 means I'm going to move it over 2. So if I were to draw this in right now, and I didn't have the negative in front, which I do, so this is an incomplete version. I'll erase it here in just a second. It would look something like this. That's where I would be. I'd take the whole graph, I'd move it 2 to the left, I'd be done. But I'm not done because there's a negative in front. What does the negative in front of the graph do to a graph? It inverts it. Does it flip it up and down, or does it flip it left and right? It flips it up and down. Okay, so anything inside affects how it flips or shifts left and right. But this is on the outside. It's not grouped inside with x, it's in front of it. So since it's outside and it's in front of x, it's going to affect y values. So it's going to flip it up and down. And as I mentioned before, you have your calculator. You could just sketch this, you could in your calculator really quick just to confirm, oh, yep, that's right. I remembered it right. It is definitely an up and down flip. So it's not actually going to look like this. It's going to look like this. Now, it is important to realize that it really does have an x-intercept where I'm marking it, right? It moved from positive 1, 2 to the left, so now it's at negative 1. That's not just happenstance on this particular graph. That is how it's actually affecting it. It also asks us to state the domain. So what is the domain of this function? And there's several ways we can write it, and we'll write it a couple of ways anyway. Domain means x values, remember? So what's the starting sort of spot of my x values? It's negative 2, right? It shifted from 0 over to negative 2. So one way to write this is that you could say that x is greater than negative 2. Now, that's not the kind of notation we typically use in a calculus course. It's an inequality notation. We typically use interval notation, and we would write that our domain would actually be from negative 2 to infinity. We would put a parenthesis on negative 2 because it can't equal it. There's an asymptote there. And infinity is a concept, not a number. So we can't equal infinity. We put a parenthesis there as well. Okay? WebAssign is going to force you, probably going to force you to do it in interval notation. I don't really care if you're doing something written for me if you write it either way. This is not what we're focusing on. This is not calculus. This is algebra. So pick your favorite when you're writing it down and go with it. But I think that WebAssign will probably tell you to do it with intervals. Okay, any questions on that? Okay, now let's look at some logarithmic properties. Again, you've seen these before in an algebra course before now. These are some properties of logs. Some of them are very obvious from the graph. I'll mention those, and some of them are sort of an extension beyond that. But the first one is one of those. The natural log of 1 is equal to 0. That's the x-intercept, right? The original x-intercept over here was at 1, 0. So when x is 0, y is 1. I said that wrong. When x is 1, y is 0. There we go. So that's the first one. The second one is an extension. This isn't visible, or at least not very intuitive on our graph, but the natural log of e is 1. Now, you might remember, and again, it'll come up in a little bit as well, but the natural log of e, or we'll just say natural log of x. Let's go with that. Natural log of x, another way to write natural log is to write it as log base e. Does that look familiar at all? It's not a very good e, but... So another notation, it's just another notation for it, is to write it as a subscript. It is a subscript. It's not that the x is an exponent on the e or something. That's not what's happening. It is a subscript. So natural log, ln, right? Think Latin, right? Words, Spanish does this too, right? Where adjectives and nouns are flipped the way we do them, right? Like we say pretty girl and you would say girl pretty. That's what you would do in Spanish. It's like that with Latin too. So the natural log is coming before ln. That's why it's happening. It's common, it's a commonly used log. So it has its own name. That's why it's using the ln. What I wanted to mention here is that if we rewrite the natural log as log base e of e, you can see how they're sort of looking like they're going to cancel out, right? The base and the e next to it are the same. This is going to happen and show up on some other logs later. The next three are ways that you can rewrite logs either in more of an expanded form and more of a condensed form. These are going to help us a lot when we get to derivatives. A lot. You're going to love these. And you're going to want to use them. So the first one says that if you have the natural log of a times b, it is the same as the natural log of a plus the natural log of b. And if you have the natural log of a over b, this is the same as having the natural log of a minus the natural log of b. And if you have the natural log of a with an exponent, that exponent can actually be brought to the front, right? And it become a coefficient multiplier, kind of like what we do with derivatives, but it's not decreasing it by 1. It's just completely moving, right? And it's going to be the n at the front and the natural log of a. So the reason that this is very helpful is because take a look at what would happen if you tried to take a derivative of natural log of ab, right? You would have a chain rule. The inside has a product, and you'd have to do the derivative of that. But if you can separate them with addition, there's no chain rule needed. And it will make things a lot easier. So being aware of and using log properties is going to make our lives easier for doing derivatives. So for right now, we're just going to practice a little bit of these properties, separations, and putting them back together. So in this case, in this first one, it's asking us to use the properties to expand. So expand means to break it all apart and out. Okay? So what do you notice here first is something that can be expanded. Like what do you see as an expansion you can do here? A rewriting step. We'll do it in a couple steps.
E squared.
Okay, the 3 and the e squared are multiplied, so we can separate them. So we can rewrite this as the natural log of 3 plus the natural log of e squared. That is the first thing that we would actually need to separate. There is still an exponent of 2 that's going to come to the front, but it can't happen before it's separated because that exponent of 2 is not on the 3. The exponent of 2 is only on the e. But that will be our next step. So now we can actually rewrite this as natural log of 3 plus 2 natural log of e. There is one more simplification we can do with this. Do you see it?
Natural log of e is just 1.
Natural log of e is just 1. This piece right here is equal to 1. So this actually simplifies to natural log of 3 plus 2. Okay? You're grinning.
So in my calculus class last
Yeah.
year, I was not doing that, and so it was so much more.
It was so much more complicated when you didn't do it. Yeah, I'm sure it was. Okay, let's take a look at what's next. Okay, now we're going to go the reverse. We're going to condense them back together. So why would we want to condense things back together? Well, sometimes it actually cleans up answers. That's usually when we see it used. And so we've got a much nicer version of an answer, and so we would compact them back down. So this one looks really ugly. I've got a 2 at the front. I've got natural log of x minus the natural log of x plus 1 minus the natural log of x minus 1. So there's a lot going on. The 2 at the beginning is the last thing we're going to deal with because it's on the very outside, so ignore him for now. We need to condense all these logs into a single log. Since they are all natural log, they all will be able to be condensed. As a general statement, when we are looking at these properties over here with the, this is subtraction and this is addition, and where do I multiply and where do I divide? If it's addition, it tells you to multiply, and if it's subtraction, it tells you it's going to divide. It's going to go in a denominator. So over here, we see 2 subtraction pieces. All it means is that the interiors of those logs are going to go as a denominator. So the part at the beginning is going to be on the top, and then the x plus 1 and the x minus 1 are going on the bottom because they're both subtraction of a log. So I've subtracted the log. It's going to be divided by that piece. It still has a 2 out in front, though. So what am I going to do with the 2?
It's going to turn into an exponent.
It's going to turn into an exponent. And it's going to turn into an exponent of everything that's inside of that log. So you can write that one of 2 ways. You could write this natural log of x over x plus 1, x minus 1, all of that squared. That's fine. Or if you prefer, you can write this as the natural log of x squared over x minus 1 squared, plus 1, sorry, over x minus 1 squared. We'll do them in the same order. It doesn't matter which way you write that at all. There's neither one's better than the other. So take your pick. Okay, so I'm not doing like a whole lot of examples of any of this because these are things you have seen before. And they're not calculus. We are trying to get to the calculus, but reminding ourselves of some of the algebra along the way. All right, so let's take a look then at what happens when we're trying to use these log properties. And we know something about them. And they give us ones, like natural log of 2. If you put this in your calculator, it's going to give you the same decimal it gives you here. And natural log of 3 is going to give you the same decimal. They could have given you variables here. Instead of saying natural log of 2 is equal to this quantity, they could have said natural log of x is equal to this quantity, natural log of y is equal to this other one, and we could do the same thing. So this really is asking you not to just stick it in your calculator, but to use properties to do it and the values that they've given you. So in particular, on this first one, you see division. So how can I rewrite this in an expanded form first? ln of 2 minus the ln of 3. And the natural log of 2, they give you. It's 0.06931. And the natural log of 3 is given to you. It's 1.0986. Okay, and then you're going to let your calculator subtract it. I mean, you can subtract it if you want to on paper, but you can let your calculator do it too. So if you subtract these two, what do you get? Did anybody bring a calculator with them today? Okay, did I hear that right, Elijah? Okay. So it's negative 0.4055. Yeah. Okay, how about natural log of 81? I mean, I've got to change this into something that uses either natural logs of 2s or natural log of 3s. So there's got to be a way of expressing 81 using 2s or 3s. Any thoughts?
Just divide by 2.
We can break it down and see what happens when we do. There's actually maybe a faster way of doing it. Do you know what 81 is in a really nice broken apart form? 9s. There you go. Yeah, so 81 is 9 times 9. And what's 9? 3 times 3. So 81 is the same thing as what? 3 to the 4th. Okay, so anytime you're looking at numbers that are larger and you've got the directions that are given where you've got some pieces like this is what they're looking for you to do, to figure out how to break them apart. I mean, they didn't have to give you 81. They could have given you something a little bit more interesting that had 2s and 3s in it, right? They could have said natural log of 6. Oh, okay, natural log of 6. I can break that apart. That's 2 times 3. They could have done that. Lots of other options. What would I do next? You bet. The 4 to the front. So I've got 4 and then natural log of 3. And then I know what natural log of 3 is. That was a given piece of information. Sorry, not negative. It's 1.0986. And when I multiply that by 4, what do I get? Okay. Very good. Everybody good? All right. So all of this is review from a really long time ago. Next topic actually is calculus because it's limits. If you remember, that's the very first thing that, at least at OBU, we do with calculus is limits, right? Talk about limits. So we're going to notice and we're going to consider our graph of the f of x equals natural log of x and consider the following limits. So I'm going to sketch our graph on here so that we have a place to see it again. Let me do this. All right, so here's the axes, and our graph looks something like this. And we're asked to find, on the first one, the limit as x goes to infinity. So if you'll remember, the way that I always show these is I show us drawing arrows. So if x is going to the right forever, I'm going sort of up along where these green arrows are. What y value am I approaching? Infinity. Yeah, in fact, that's one of the properties we'd listed earlier, right? That's not actually anything new. So this one's infinity. I'm going to keep it with the colors matching. What happens if I go towards x equals 0? So I'll change color. Let's use orange. So the natural log of x as x approaches 0 actually means that I'm going closer and closer to the y-axis, along where that orange is going. What y value am I approaching? Negative infinity. I shouldn't say that. I'm sorry. I did part C here. This one's negative infinity. That's what I was doing. What happens on, we'll come back to the one I skipped. What happens on the bottom one? What is the limit as x approaches 0 from the left? It's undefined. It doesn't even make any sense. There's nothing on the left-hand side of this graph, right? I cannot get close to 0 from the left-hand side. So this one is actually, like you said, undefined. Or if you prefer, you can write it does not exist, D&E. And then the one I skipped, almost didn't, right, is actually talking about what happens when you come from both directions. So when you're looking at a limit that comes from both directions, what it means is it actually has to have the same value in both directions, and ours doesn't. It doesn't even have a value in one of the directions at all, much less having the same value. So up here, this one would also be undefined, or it does not exist. So we can use these ideas and we can talk about what happens on a graph that's also been manipulated or shifted. So when we take a look at this graph, we talked about this kind of shifting before. What does this graph tell you has happened? Not the graph. What does the equation tell you has happened to this graph? Yeah, so this one is shifted to the right 6. So roughly speaking, in terms of a graph, I would move this over 1, 2, 3, 4, 5, 6. That's actually my asymptote there. And the graph looks something like this, right? So if I'm looking then for the directions in this problem, which says that I'm taking the limit as x approaches 6 from the right, this is 6, right? And if I'm approaching it from the right, this is how I'm moving. And what is it? It's negative infinity. Now, what if this graph had been like the one that we did with our phase shift before? Let me go back over here with this one we had. Yeah. What if it was this one? What if it had this graph and it said the limit, I'll make it up on this one, the limit as x approaches -2 from the right. I'm just going to call it f of x, so I don't have to write it down. What would I get if I were approaching -2 from the right on this one? -2 from the right. So here's -2. Yes. I would be actually approaching a positive infinity, right? Because this graph flipped upside down. So it's not always negative infinity. If the graph flips, it could also change that to being, in this case, like positive infinity. So I didn't write it, but maybe I should have. There we go. Okay, so let's get to some calculus. Derivatives. So what happens when we're working with these for derivatives? Well, what we're actually trying to take the derivative of is the natural log. But that's a beautiful thing because the whole way we defined what the natural log was in terms of antiderivatives, right? What we actually wrote down at the beginning was that the natural log of x is the integral of 1 over x. That's what we wrote. It might have a plus c, but that's sort of irrelevant to the topic of conversation. It is the antiderivative of 1 over x. So if I want to find the derivative of this, what happens when I want to find the derivative of an antiderivative? You get back to where you started. It's 1 over x. Right? We actually had fundamental theorems of calculus, the second fundamental theorem of calculus at the end of Calc 1 that talks about this. The derivative of an antiderivative is the function itself. Right? It's like saying, what if I multiply by 6 and then I divide by 6? Well, nothing changes, right? Take an antiderivative and then I take a derivative, nothing changes. Now, sometimes we have plus c's that come in and out depending on which direction we do that in, but nothing is going to change in terms of the function itself. So when we're looking at these functions, and we see f of x is natural log of x minus 1, we're going to get 1 over what? Somebody say it. Yeah, 1 over x minus 1. Now, x minus 1 is not just x, so we do need to pause for a moment and ask ourselves, well, what do I see here? I really have a chain rule. It's just not a very exciting one. Because what's the derivative of x minus 1? It's just 1, right? Derivative of x minus 1 is just 1. So I'm going to write it there just to remind you that we did it, but it doesn't actually change it. It's just 1 over x minus 1. Okay? Now, on part B here, it matters. It will matter on part B that we remember that there's a chain rule going on. Now, I want to show you that there's 2 ways that we can do part B. One option is that we can do this directly, which means that we do the derivative is 1 over. It'd be 1 over the inside, which is x over x squared plus 1. And then we'd need the derivative of x over x plus 1, which means we're going to use what? What do I have to do to find the derivative of x over x squared plus 1? The word you're looking for is quotient. It's a quotient rule, right? Because it's division. It's a quotient rule. Well, what's the quotient rule? Well, it's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, which is 2x, over the denominator squared. Are you having fun? That looks terrible, doesn't it? Do you want to see an easier way to do it? Nobody. You just all want to do it that way. No? Okay. Just checking. All right, let's change colors and let's do it a different way. So I'm going to use this kind of dark red. Do you remember we took a little side adventure back into a little bit of algebra too? And we said there's these properties of logs, and we could make use of them if we'd like. In particular, what if we write this as the natural log of x minus the natural log of x squared plus 1? There's no more there's no more quotient rule, because there's no more quotient, right? That's already a leg up from where we just were. So what is, if I go from this route down here, what is the derivative of the natural log of x? Don't overthink it. 1 over x. Okay, whoops. What is the derivative of the natural log of x squared plus 1? There's a minus sign here. Don't overthink it. How's it going to start? 1 over x squared plus 1, right? Okay, that's the first part. It is a chain rule, though. I do need to take the derivative of the x squared plus 1. What's the derivative of x squared plus 1? It's just 2x. Okay, so I do have to do that part of it. But there's no quotient rule going on here anymore. And the only thing I would need to do to sort of clean this up is to write this as 2x over x squared plus 1. And this would be a very viable way of having my derivative that avoids a lot of the mess. So these properties of exponents, you need to use them. Now, if you wanted, or if you were asked, could you combine these fractions back together? Sure, you could. You get a common denominator, we subtract the numerators, all that stuff, right? Generally speaking, you're not going to need to do that, but if it did ask you to write it as a condensed expression, right, all in one fraction, you would need to do that at this point, okay? All right. One more, and then we'll pause for today. All right. This one cannot be broken apart. We have addition inside of that log, not multiplication and not division, right? So we really do have to do this with the mess that's there. So let's get this one done, and then we'll stop for today. So we will start by writing this as 1 over the interior of the log. So 1 over x plus the square root of 4 plus x squared. Then we need the derivative of that. Well, the derivative of the x is 1. The square root of 4 plus x squared is a chain rule, right? It's the same thing as having 4 plus x squared to the 1/2. So we're going to bring the 1/2 down. We're going to rewrite the inside. And we're going to decrease the exponent by 1. 1/2 minus 1 would be negative 1/2. And then we do the derivative of the inside, 4 plus x squared, to give us 2x. Okay, so log properties are not the end-all be-all. They don't always help us. They don't help us on this one. And we do need to clean this up. Now, some of it cleans up pretty nicely. Take a look here. We actually have this 2 and this 2 cancel. That's kind of nice, right? So that's at least something. Over here we have the same that we had to start with. And over here we have 1. We have plus the x, and then the square root becomes the square root on bottom because it's a negative exponent, like that. Something really cool is about to happen. Something lovely, unexpected perhaps. I'm going to get that part that's in parentheses to have the same denominator, but its denominator clearly needs to be pretty much the same thing it already is, right? The other part of it. So this denominator is going to be the same thing, square root of 4 plus x squared, which gives me the numerator is 4 plus x squared. Now, if I combine this into a single fraction, take note of what's going to happen. Do you see something nice? Yeah, this and this are identical, so they cancel out. So this all reduces, maybe a little bit unintuitively, to 1 over the square root of 4 plus x squared. And this is a good point for me to make right here as we close. There's no need to, quote unquote, rationalize that denominator. And the reason that there's not is because depending on what x is, it might already be a rational number. We rationalize when we have a number underneath a square root, not when we have variables under square roots. So don't go doing more work than you need. This is perfectly fine as is because it's not just a single number underneath the radical, but it's a variable expression underneath the radical. Okay, so we will push pause right here. You will not have any homework that will be due next class period, which would be Tuesday. We will finish this lesson on Tuesday. This assignment will be due next Thursday. If you would like to start it, though, nobody is preventing you from doing that.